think about your moon city. And we learned that on the moon, there is helium-3 on the surface of the moon. We have the periodic table that was chewed by Brutus. But helium is over in this corner. Remember here? Helium. And helium has a 2. Its atomic number is 2. So remember, that means it has 2 protons. Its mass number, or atomic mass, is 4. So that means it has 2 neutrons. That's the normal helium. However, helium-3 is not the normal helium. It's called an isotope of normal helium. So isotopes are atoms that have a different number of neutrons. They're still the same atom, however, the neutron number changes. So normal helium has 2 protons. So we're going to say the white balloons are the protons, remember. P. Okay. Normal helium also has 2 neutrons. The neutrons are going to be the black ones. The black balloons are the neutrons. So a normal helium atom then, in the nucleus, looks like this. It has 2 of each. However, in a isotope of helium-3, it does not have that neutron. It has 1 neutron. Protons are still the same, because if you change the number of protons, you have a different atom entirely. Okay, so this is still helium. How do I know it's helium? Because it has 2 protons. So the number of protons indicates the type of atom you have. If I take a proton away, it's no longer helium. This is hydrogen. Right? So helium-3 looks like this. This is an isotope of helium. This is what's found on the surface of the moon. This is in the nucleus now. We're looking at just the nucleus. We're not looking at the electrons. Remember, the electrons go around the nucleus. If we look at hydrogen on the periodic table, here we go back to the periodic table. Hydrogen is all the way up here. Hydrogen has a 1 at the top. That means its atomic number is 1. It also has a 1 for below it. So mass number is 1 also. So if the mass number and the atomic number are both 1, on average, it really doesn't even have a neutron. So a hydrogen atom in the nucleus would just be a proton. This is a normal hydrogen atom. However, there are isotopes of hydrogen, just like there are isotopes of helium, isotopes of other atoms. And that isotope that we can use for nuclear energy looks like this. So it has 1 of each, and this is called deuterium. You don't really have to know the name of it, but it has 2. So this is an isotope of hydrogen. How do we know it's hydrogen? It has 1 proton. Okay, so the protons, remember, indicate the type of atom. Okay, so here we have this is a hydrogen isotope, deuterium. And here we have helium-3. So we have 2 isotopes. This one's helium, this one's hydrogen. In nuclear fusion, they fuse together. Energy! When this happens, there's energy released. And what happens then is normal hydrogen's produced. This is a normal hydrogen, and a normal helium is produced. Look at that. This is nuclear fusion. So again, nuclear fusion, we're starting with 2 isotopes. Nuclear fusion, we're starting with 2 different isotopes. They come together. end up with one normal hydrogen and one normal helium. So look at that. That is nuclear fusion. Energy is released. That energy then can be used. So this is what we're working on, the future of our energy on Earth. And this is what they're thinking of using the moon, the resource on the moon, helium-3, to provide energy. Fission splitting. So this is when you start with a massive atom and you split the nucleus. So large atoms. So if you think of periodic table, they have the heavy atoms at the bottom of the table. Uranium, plutonium, large atoms. If you split the nucleus, energy is released. And that is nuclear fission. And this is what we're using here on Earth right now. But it is causing problems because in that process, there's a lot of nuclear radioactive waste that is created. So there are environmental problems to using nuclear fission. However, nuclear fusion is supposed to be considered a potential source of clean energy. Nuclear potential energy, this is energy stored in the nucleus. In the nucleus, the atoms. So this is an energy that is between the protons and neutrons in the atoms. And this can be released in two ways. Here we have the nuclear potential energy, just energy stored in the nucleus of the atoms. Two main types, nuclear fusion, combining the nucleus, one atom with the nucleus of another atom. Just like we look at helium-3 with deuterium, which is the isotope of hydrogen. So hydrogen, helium-3, producing normal hydrogen, normal helium. That's an example, nuclear fusion. Nuclear fission is splitting atoms. So when you're starting with a larger atom, you're splitting the nucleus into smaller atoms. The third type of potential energy is elastic energy, also called stored mechanical energy. Okay, so elastic energy is also known as stored mechanical energy. Have you ever been on a trampoline? Springs are in a trampoline. When you land on the trampoline, springs compress, push down. You've applied a force. That is creating, there's stored energy in that spring when it's compressed. That is called the stored mechanical energy or elastic energy. So compressed springs, it's energy waiting to happen. Energy is going to be released when that spring is released. If you think of the spring in your, like a ballpoint pen, wind-up toys that have springs in them. So springs are really examples of this stored mechanical energy. It is stored, right? It's going to be transferred to kinetic energy when that force is not applied to it anymore. So when release that force, so transform energy from the stored potential to kinetic. So this is elastic energy. Last type of potential energy is gravitational potential energy. And that's really due to gravity. So it's potential energy due to the position of an object in relationship to the Earth. So the higher up you are from the Earth, the more distance, the more potential energy. That's why on a roller coaster, you're at the very top, you're like, ah! You're at the top, like the main lift hill. Like, you know how you get up there and you have to wait a little while, keep you in suspense. When you're at the very top, you have maximum potential energy. But it's gravitational potential energy. So on Earth, there is a gravitational force that accelerates at a rate of 9.8 meters per second. This is the acceleration due to gravity. So lowercase g, acceleration due to gravity. On Earth, it's 9.8 meters per second squared. So that means if I'm at the top of the roller coaster let's say. And we're just going to free fall, just going straight down. Let's say there's no resistance, so you're in a vacuum. The rate in which you speed up as you go down is 9.8 meters per second. So the first second you drop, you would travel 9.8 meters. The second, it would be 9.8 meters plus 9.8 meters. So you would double it. The third second, it would be triple. So as you're going down the roller coaster, like, it gets faster. The ride speeds up. And this is why it's per second squared, because if it were just per second, that would be the distance the object would travel per second. But it speeds up. So the first second is 9.8. Second is going to be 9.8 times 2. So this is the acceleration of gravity on Earth. So the acceleration of gravity on Earth is 9.8 meters per second squared. On the moon, it's different. When we're looking at potential energy and really gravitational potential energy, there's a formula for gravitational potential energy. You'll see it like this, where it's just potential energy with the G indicating this is gravitational potential energy. And this equals the mass of the object. So if it's the roller coaster, how much does that roller coaster weigh? The mass. Times the acceleration of gravity, lowercase g, 9.8 meters per second squared, times the height. Okay, so the mass is going to be in kilograms, height, meters. So you can calculate the gravitational potential energy of a roller coaster if you know the mass of the roller coaster, and we know this is 9.8, and you know the height of the roller coaster. And you can see the bigger this number is, the higher you are on the roller coaster, the more potential energy you're going to have. The more mass, the more potential energy you're going to have. Right? If I increase this number is going to increase. If I increase this number, that number is going to increase. So gravitational potential energy it depends on the mass and the height. So the more mass, the more potential energy, the more height, the more potential energy. And gravitational potential energy is a form of potential energy. So it's energy that is due to the position of the object or the height. So again, as a review, potential energy, stored energy, energy waiting to happen. One type of potential energy is chemical potential energy. This is energy stored in chemical bonds involved in chemical reactions. Second type of potential energy is nuclear potential energy. This is energy stored in nucleus of the atoms. It's involved in nuclear fission, nuclear fusion. Third type of potential energy is elastic potential energy or stored mechanical energy. You think of the wind-up toys, springs, trampoline, pressed spring, there's energy in that spring. If you're jumping on your bed, there's stored energy in the springs, in the mattress. So when you compress the spring, there's energy in there. And the fourth type is gravitational potential energy. So you think of a roller coaster ride. Maximum potential energy at the top of the hill. So energy rocks.